Ever just look around at, well, everything? The chair you're sitting on, the air you're breathing, even your own hand, and wonder what it's really made of? Like on the deepest, most fundamental level? Well, today, that's exactly what we're going to do. We're going to deconstruct the world around us, breaking it all down to its essential chemical building blocks. Let's get right into it. So here's the game plan. We're going to start super small with a world of tiny particles. Then we'll zoom in on the atomic blueprint itself. After that, we'll see how all those atoms get organized. Then comes the fun part, how they all stick together to make stuff. And finally, we'll look at the tools chemists use to, take it all apart again. All right, first things first, we have to get one basic rule down because it's the foundation for everything else. And the rule is this. Everything, and I mean everything, is made of tiny little particles that are always moving. I mean, we all know what a solid, a liquid, and a gas are, right? You've got an ice cube, a puddle of water, and steam. Easy. But what's actually physically different about the particles in each one of those states? What's going on down there? Okay, so check this out. In a solid, all the particles are crammed together in this super organized grid. They're still moving, but they're just kind of jiggling in place. The forces holding them are just too strong. Now look at a liquid. The forces are weaker, so the particles can break free and just slide all over each other. That's literally why liquids can flow. And then you've got a gas. At this point, the particles have so much energy they've completely broken free. They're just zipping around randomly with tons of space between them. So really, it all just comes down to spacing and energy. That's it. And yeah, there's a fancy name for this whole idea, the Kinetic Particle Theory. All it means is that everything is made of particles that are constantly moving. The big takeaway? If you add heat, you add energy, and those particles start moving faster. That's how you turn that solid ice cube into liquid water and that liquid water into steam. Okay, so we keep saying particles. But what are these particles really? What's the fundamental piece? Well, to figure that out, we have to zoom way in on the most important building block in the entire universe, the atom. So if the atom is the ultimate Lego brick, what's the Lego brick itself made of? What are the even smaller pieces that give each atom its own unique personality? Turns out, it's just three things. You've got the proton, which is positive, the neutron, which is, neutral, no charge at all, and then the super tiny electron, which is negative. And get this, look at the mass. If a proton or a neutron was a bowling ball, an electron would be like a single grain of sand. The two heavyweights, the protons and neutrons, hang out in the middle, and the incredibly light electrons just zip around the outside. So, what makes an atom of gold different from an atom of helium? It's this one number, the atomic number. It's nothing more than how many protons are in the atom's core. That's it. It's literally its ID card. If you change the number of protons, you've changed the element completely. No exceptions. Then you've got the mass number, and this one's pretty straightforward. It's just about an atom's heft. You just add up the number of those bowling balls, the protons and the neutrons, and that's your mass number. Simple as that. And this is where it gets really interesting. So if the number of protons is the unchangeable ID, what happens if you mess with the number of neutrons? Well, you get an isotope. It's still the exact same element, because the proton ID is the same, but it weighs a different amount. Think of it like a heavier or lighter version of the same person. This is exactly what carbon-14 is, and it's how we can date ancient artifacts. Pretty cool, right? So we have all these different atoms with different IDs and different weights. How in the world you keep track of all of them? Well, luckily for us, chemists came up with one of the most elegant and powerful organizational charts ever created, the periodic table. The absolute genius of this table is how it's organized. Those vertical columns are called groups, and you can think of them as families. Every element in the same column acts in a really similar way. Then you've got the horizontal rows, which are called periods. An easy way to think of this is that electrons orbit the atom in layers, kind of like an onion. Well, everything in the same row has the same number of layers, or shells. The whole system is just brilliant. So let's look at one of these families. Group 1, the alkali metals. These things are wild. They're metals that are so soft you can literally cut them with a knife. And they are so incredibly reactive that you have to store them under oil just to stop them from freaking out and reacting with the air. And the further you go down the column, the crazier they get. Okay, now let's jump all the way to the other side of the table to group 7, the halogens, a totally different family. First off, they're diatomic, which is just a fancy way of saying they don't like to be alone, they always travel in pairs. And unlike the alkali metals, their reactivity actually goes down as you move down the family. They are desperate to steal just one electron, which makes them super reactive, but in a totally different way. All right, we have the pieces, we have the instruction manual. Now for the main event. How do these individual atoms actually stick together to build, well, everything? I mean, that's the big question, right? What's the chemical glue holding the universe together? How do you get from a single atom to a tree, or a car, or us? The answer is all about bonding. And it really boils down to two main strategies. The first is ionic bonding. This is where a metal literally just gives an electron to a nonmetal, a total transfer. This creates a super strong connection, which is why something like table salt has a crazy high melting point. The other strategy is covalent bonding. This is where a bunch of nonmetals decide to share their electrons. It's more of a team effort. This bond is weaker, which is why things like water boil at a much lower temperature. So just remember that. One is a transfer, the other is sharing. Now, that moment, that act of giving or taking an electron in an ionic bond, it's a huge deal. It creates something totally new called an ion. The atom isn't neutral anymore. It now has an electric charge. And this isn't just some abstract concept. This is literally how batteries work and how the nerves in your brain fire. It's absolutely fundamental. But wait, what about a chunk of pure metal, like a copper wire? What's holding that together? Well, metals have their own special trick. All the atoms pack together and just release their outer electrons into this big shared pool. They create this amazing sea of electrons that just flows freely through the whole structure. And that is the secret for why metals are such amazing conductors of electricity. It's that free-flowing sea. Okay, so we've spent all this time building things up from individual atoms. But as you can imagine, a huge part of chemistry is also about taking things apart. And understanding all those properties we just talked about is the key to doing it. And chemists have this awesome toolkit for doing just that. Each tool is designed to exploit a different property. For example, filtration is exactly like making coffee. You use a filter to separate the solid coffee grounds from the liquid. Simple. Or if you have two liquids mixed together, you can use distillation. You just boil the mixture, the liquid that boils first turns into a gas, and you just catch it. See? Every single one of these techniques is just a clever, practical use of the basic rules we've just covered. So when you really get down to it, everything around us is just a specific arrangement of atoms held together by a specific kind of chemical glue. So I want to leave you with this thought. Now that you know the fundamental rules of construction, you can look at the world a little differently. Don't just see objects, see possibilities. So what will you build? Or what will you take apart?